So this time we'll do something really fun. We're going to derive the Einstein field equations for gravity. Okay, so we started with Maxwell's equations for electricity and magnetism, or electromagnetism, and this time we're going to do the same for gravity. So let's recall the geodesic equation. The equation for paths which extremize the length of a world line. d2 mu d tau squared plus gamma mu nu lambda which was just that, where gamma is the connection. So the gamma mu nu is the Christoffel symbol we defined before. The connection. And by the way, when you write this down, geometrically what it means is that d by d is that, i.e., d by d tau u mu equals 0, where that capital D by d tau means covariant differentiation along a curve, right? Where this is defined to be d by d tau u mu plus, plus gamma mu nu lambda u nu dx lambda d tau. And so obviously, so d by d tau remember, covariant differentiation along a curve is defined this way, that we say something equals 0 if u mu is parallel transported along x mu of tau. Okay, so obviously the geodesic equation states that the forward velocity u mu equals dx mu d tau is parallel transported along the world line. Okay, so geodesic is just telling you that the forward velocity is parallel transported along the particle's world line. Now, for massive particles, we defined tau by g mu nu dx mu d tau dx nu d tau is -1. one can check that d by d tau of g mu nu of x of tau So you can check that the geodesic equation implies that this quantity is constant along the curve. And so everything here is consistent. We have a constraint. This is called a constraint. And we have an equation of motion. And the two of them are compatible with each other. Okay, so when you pick initial conditions for the particle's position and for velocity, you have to ensure you're consistent with this equation. If you're consistent with that equation at some initial value of tau, then the evolution equation will preserve the relationship. Okay, so these two equations describe the particle's motion under gravity. Let's call that 1 and 2. 1 and 2 describe the motion of a test particle of any mass. I'll explain what test particle is in a moment under gravity. The idea of a test particle is that the mass is not big enough to really change the gravity, to affect the gravity itself. Okay, so, if I drop this piece of chalk, it's not really changing the gravitational field due to the Earth. And so the idea of a test particle is it's traveling in a fixed metric, not affecting that metric. But if that's the case, if the particle is not affecting the metric, then it really doesn't matter what the mass of the particle is. And you can easily see that because the action for the particle was just minus m times the length of the world line. So the mass is just an overall constant and doesn't come into the equations of motion at all. Okay, so that's the motion of matter or particles under gravity. Let us now understand this equation in the Newtonian limit. So the Newtonian limit is described as follows. We say that the metric is equal to eta mu nu plus h mu nu, where the magnitude of h mu nu, all the components of h, the magnitude of all the components of h are much smaller than 1. Okay, so these are what we call weak gravitational fields. Okay, so the metric is nearly Minkowski space. There's just a small correction. Furthermore, we will assume that the velocity of the particle dx dt for particle is also much less than 1. And I'm working in units where c equals 1. So the particle is very non-relativistic. So we've got a non-relativistic particle moving in a very weak gravitational field. And furthermore, we're going to assume that for the energy, we assume that the stress energy T mu nu creating the gravitational field has Tij much less than T naught naught. Okay, now what does this mean? We haven't really discussed the Tij very much, but I did tell you that this defining property really of a stress energy tensor is that it's conserved. Okay, and this gave rise to the conservation of energy, that d naught T naught naught plus di Ti naught equals 0, for example. So the rate of change, this was the energy density, rho energy, let's call it, I think I called it rho E. So the time derivative of the energy density is the divergence of something. So rho E dot d by dt rho E was minus divergence of something. We called it J. And what this means is if I integrate this around some volume V, then d by dt, then ordinary derivative d by dt of integral d3x rho E is equal to minus this guy, and now I use the divergence theorem. So I've got some volume V surrounded by a surface S, and this is ds dot J. And this is the conservation of energy, because if I think of some volume, large volume, such that nothing is leaving or entering it, then the total, oops, it's hard to see that. Let me push that up. Think of some large volume where nothing is leaving or entering, then the energy inside the volume, which is that quantity, is going to be conserved. So if we stare at this equation, d naught T naught naught equals minus di Tij Ti naught. What this equation is telling us is that the change in the energy density at any point is just the flux of momentum density at that, is the divergence of the momentum density at that point. And furthermore, we have this equation, d naught T naught I is equal to minus dj Tj I. Right? That's just the I components of the equation on the top line. So this is saying that the time derivative of the momentum density is the divergence of something else. What do you think the something else is? You see, this is all about how you move things around in the world. If I want to move some energy around in the world, I have to have some momentum. It's the only way I can move. That's what the first equation is telling you. Right? If I have a lump of energy and I want to change the energy density, the only way to do it is to have some momentum so that this guy moves. That's the first equation. Here's my energy. This is my momentum. Likewise, if I have some momentum moving along, the only way to change the momentum density is to have this being non-zero. What is that quantity, the Tij? What is it physically? I mean, how do I get something in motion, right? I want this guy to be in motion. How do I get it to move? I push it. Okay, so the Tij are the forces. And that's called a stress tensor. Tij equals the spatial stress tensor. Right? And that's how we move things. We apply stresses. You notice these equations don't really constrain the stresses at all. The Tij doesn't obey any equation at all. You're free to put any stresses you like on anything. And the consequence of those stresses will be that momentum is created. The consequence of creating momentum is that energy can be moved around. Okay, so for example, for a perfect fluid, e.g. for perfect fluid in its rest frame, Tij is the pressure. So what we're really assuming here, in this case, would amount to, so our assumption is that the pressure over the density is much less than 1. Okay, so in Newtonian theory, you generally neglect pressure as a source of gravity. And pressures in the real world are quite small. I mean, in the gas in this room, what's the pressure, right? The density, the energy density for gas in a room, the energy density is just the number density of particles, number per unit volume, times their mass, times c squared. Right? The particles are sitting there with their mass. Not quite right. This is plus n plus 1/2 mv squared. That's their kinetic energy, right? We've derived that, actually. We derived that the energy of a particle is mc squared plus 1/2 mv squared, right? If it's moving at energy v. So this is the energy density of the gas in this room. And this is the usual formula you use in ideal gas. And what's the pressure? The pressure for the particles in this room. You probably did this quite a while ago. If you can only remember it. There's a 1/3 in it. The particles banging around in this room, what's their pressure? Do you maybe remember this? Sort of? Okay, that's the pressure. And so that you see that the pressure divided by the energy density is certainly much less. So P over rho is 1/3 V over C squared, which is much less than 1. What's the velocity of a particle in this room? Particle in the gas in this room, roughly? How fast do you think the molecules are moving? Speed of light? All right, I'll leave you to look that up. Okay, so we're going to study the Einstein equations with these 3 assumptions. Okay, so our idea, we want to look at objects like the sun. We want to look at smaller objects like the Earth. Right, that will be our test particle. and we want to see how does this move. If we can understand that, then we can do Newtonian gravity. Or this might be the Earth, and this might be a projectile. So we're just going to reproduce all of Newtonian gravity from geometry. Finally, I want to make another assumption. We're going to assume that the time derivative of the metric is 0. In Newtonian gravity, the idea is that the gravitational fields are fixed. If you fix the objects causing the fields, like the sun, then the field around it is just constant in time. So it's going to be easiest to study this situation and try to infer what the relationship is between geometry and Newtonian physics in that situation. Later we can generalize it. In fact, we will generalize it because we're going to study gravitational waves, where, of course, I can't make that assumption. So a little bit of algebra. If G mu nu is eta mu nu plus H mu nu, what is G mu nu with upstairs indices? So just make a guess.
Eta minus H.
Eta minus H. Okay, so obviously eta mu nu minus H mu nu. Why? Well, the inverse of 1 plus x is basically 1 minus x. 1 over 1 plus x. Taylor series is 1 minus x, if x is small. What does this mean? So this was the definition of H mu nu, right? I just took G, so it's approximately, with downstairs indices, approximately eta with a little correction. H mu nu with upstairs indices, the only thing I have around is eta, so it must be eta mu alpha, eta nu beta, H alpha beta. So that's the only thing that really makes sense. And those etas will make sure you have the right minus signs. So we can check that. Let's check that. So eta mu nu plus H mu nu. And now I'm going to multiply by this. So I contract the nu index. Nu, let's call it beta. Minus, and then here I have eta nu, eta beta, lambda delta, H lambda delta. And we only need to work to first order in H, because H is much less than 1. So obviously what I get here is delta mu beta, that's multiplying these two terms. And then I multiply this by that, and I get plus H mu beta. And then so that was this term, and then I multiply these two terms. Okay, so this will give me delta mu lambda. Delta mu lambda times H will give me H mu delta. And then I have H delta beta. So that raises the, H mu. This raises the delta index, beta. There's a minus sign. So this is 0 to order H squared. Okay, so that's the inverse metric, which we will also need. And then we have d tau is square root dt squared minus dx squared. Right, we're going to be using the geodesic equation, so we need to reinterpret tau in terms of t. And this is approximately dt times 1 minus 1/2 dx dt squared. So if the velocity is small, if v is much smaller than 1, this is approximately dt. So then the four components of the geodesic equation are d2xi d tau squared, which is approximately d2xi dt squared, is approximately, so the geodesic equation is the very first one up there. I take the gamma term over to the right-hand side, and I'm going to use the fact that the dt d tau is approximately 1, and the dx d tau I can forget about. Okay, so this gives me minus gamma I 0, 0 times dt d tau squared, and this is approximately minus gamma I 0, 0. Okay, so this is my acceleration equation. This should be F equals ma for gravity. Here's the acceleration. Here's the force divided by the mass. And likewise, I have d2t by d tau squared is approximately actually, let me just leave this as d tau squared. There's a little bit of a subtlety in changing from t to tau. So let me leave that as d tau squared. And this d2t d tau squared is minus gamma 0, 0, 0 dt d tau squared. And so this is approximately minus gamma 0, 0. So we need to know this gamma. Well, gamma mu nu lambda is 1/2 g mu alpha g lambda g nu alpha lambda plus g lambda alpha nu minus g lambda nu alpha. Now, the g is eta plus h, but eta is a constant, so the derivatives give 0 on the eta. So these terms are all of order h. The inverse has an eta term and also has an h, but if I can drop the h term in here because I already have an h here. So if I kept it, I would have h squared. So I can just I can replace this one. This is of order h. All right, so that means you can drop h here, because we're not interested in terms of order h squared. So this is approximately 1/2 eta mu alpha h nu alpha lambda plus h lambda alpha nu minus h lambda nu alpha. Okay, so since d by dx naught g mu nu equals 0, we can drop any time derivatives which appear here. If any of these derivative indices are 0, we can drop them. So gamma 0, 0, 0 is 0 to first order. Let's just check that. 0, 0, 0 means this index is a 0, so the alpha must be 0. And then the other indices are 0, too. So here I have comma 0. Here I have a comma 0, and the alpha has to be 0, so that's comma 0. So everything is 0 for gamma 0, 0. But gamma I 0, 0, that's a little bit different because now this index is I, so alpha has to be the same index, I. And so these two will go because the two lower indices, the lambda and nu, are both 0, but the alpha is I. So we have minus a half eta I j h 0, 0, comma j. And that's equal to minus 1/2 h 0, 0, comma I. So raising and lowering and lowering spatial indices does not change anything. Indices does not involve any minus signs. Okay, we're raising and lowering indices now just with the eta, because I'm working to first order in H. And so I'm actually fine in writing down an equation. It looks a little bit weird. I've got the I upstairs here, and I've put the derivative index down. But provided you realize you're just dealing with spatial indices, there's no problem, and there's really no point in putting this comma up because you're just creating scope for confusion. So what this means is minus 1/2 d by dxi h 0, 0. Okay, so when I deal with spatial indices, I'm going to feel free to raise and lower them. It really doesn't change anything. So, what do we conclude from this? That d2t by d tau squared is approximately 0. So that's consistent with t being approximately, or tau being approximately t. And then we have d2xi dt squared. Well, actually, it implies, it's not just consistent, it implies that t is proportional to tau. And in fact, it implies this. So it implies that dt d tau equals constant. Okay, so the second equation implies that dt d tau is a constant. Now, if I look at the first equation, then d2xi dt squared equals minus gamma I 0, 0. Okay, because if dt d tau is a constant, then I can just divide this equation by the dt squared and cancel the d tau squareds. And this is exactly what I get. There should be a derivative there. D by dxi h 0, 0. Or d2x by dt squared is approximately 1/2 gradient h 0, 0. So let's now compare that with Newton. CF Newton. We had m d2x by dt squared. ma is the force, gravitational force, which is given by minus the mass times the gradient of the potential. So in Newtonian mechanics, we take the force to be the gradient of the gravitational potential. The force is minus the gradient of the gravitational potential. And in Newtonian mechanics, it was just a mystery why I put the same mass here and there. This was unexplained. Newton just said F equals ma. It's a law of motion. And for gravity, the force is proportional to m. And so this was the same mass, but unexplained. Okay, in Newton's theory, the force is proportional to the mass for some unknown reason. In Einstein's theory, the mass doesn't even enter, and so the acceleration is given by the gradient of something, and so we can read off what is the, and so we can read off that h naught naught in the Newtonian limit and all we've really used is that mod h mu nu is much less than 1 and v over c is much less than 1, then h naught naught is approximately minus 2 phi. Okay, just relating this equation to that. So we've learned that the perturbation of the time-time component of the metric is Newton's gravitational potential. So for a mass m, like the Earth or the Sun, h naught naught is approximately minus 2 gm over r. So if I have some mass m, then I know from Newton's theory what phi is at a radius r. I know the gravitational potential is minus gm over r. So h is plus, h naught naught is plus 2 gm over r. Of course, we've cheated here because we just used Newton's theory to calculate phi, and I just inferred what the metric must be. But what I really want is an equation that will give this without cheating. I need an equation for the metric, and that will be Einstein's equation. But before we do that, let's just put some units back. I set c equals 1. Okay, now if you can always restore the speed of light by making sure the units are right. In any system of units, h is dimensionless, right? Because eta is dimensionless, and h comes with eta. So it doesn't make any sense for h to have any dimensions. Eta is just minus 1, 1, 1, 1 in any coordinates. So this is dimensionless. What are the dimensions of that quantity? Gm over r.
C squared.
C squared. It's a velocity squared, right? And you know that from Newton's equation that Gm over r, or from basic undergrad physics, is that Gm over r is an energy per unit mass, right? This is the energy. And then the kinetic energy is mv squared. So you know that Gm over r must have units of v squared. And so it's obvious that if I left the c's in, they should come in like that, because h naught naught has to be dimensionless. So, so actually, g naught naught is minus, and then 1 minus 2gm over rc squared. All we know is that it's approximately that when the correction is small. Now, as we'll see when we do black holes, this turns out to be the exact result in a particular coordinate system, in short shell coordinates. And you already see something funny is going to happen when you go to radii small enough that this cancels. Then it looks like g naught naught vanishes. Okay, and that may be problematic if the metric can't be inverted, for example, if one of the entries is 0. It will all turn out to be fine, but it is indeed very dramatic when you go. So this suggests something funny happens when you go to small enough r. Suggests something strange happens for r less than 2gm over c squared. This is called the short-shelled radius. Okay, and very, very crudely, it's the radius at which the h naught naught gets big. And really interesting things start to happen. Okay, you're well away from the Newtonian regime. Okay, we derived this in linear theory, so we can't really trust the formula when this becomes true, but it's suggestive. Now let's give some examples of h. So on the surface of the Earth, how big do you think h is? How big is the perturbation from flat space on the surface of the Earth? Make a wild guess. Are we very close to flat space in this room? It's reasonably close. Okay. 10 to the minus 10. Wonderful. That's a very wild guess, and it's very accurate. So that is 10 to the minus 9. Okay. The correct number is about 10 to the minus 9. What about the sun? A little bit more extreme. The gravity is stronger. There it is about 10 to the minus 6. Let's go to a white dwarf. That's a cold, super dense star. That is 10 to the minus 4. And what about on a neutron star? How big is h naught naught? Wild guess.
10 to the minus 1.
10 to the minus 1, yeah. And what about a black hole? 1. Okay, so you see all these objects in the universe, and as the gravitational fields get stronger, we get towards the regime where Newtonian gravity begins to fail. H naught naught is not a small number. And so it's pretty interesting. Even for neutron stars, you're going to see some very interesting deviations from Newtonian gravity. And as I said, that will be announced in less than a month's time. So I guess we can't wait. Okay, so that was just showing you that the geodesic equation gives you everything in Newtonian gravity, providing you do the following cheat And whatever the Newtonian gravitational potential is, you stick it into the H naught naught. All right? All of Newtonian gravity is just the geodesic equation where H naught naught is replaced by phi. So that's a good start. But let's now get rid of Newtonian gravity altogether and replace Newton's equation for phi with a general relativistic equation, which will be Einstein's field equation. So in Newton's theory, phi g of x is determined by solving Laplace's equation, Poisson's equation, where this is the mass density. Okay, so in Newton's theory, you get the gravitational potential by solving this equation. It's a bit like Maxwell's equation, but with a minus sign here. In one of, let me see. Yeah, it's a bit like the equation we use to get the electrostatic potential from the charge density. But here it's the mass density. And this is completely equivalent to saying phi is the sum over a set of particles of g minus g m x minus xi. Okay, why? Because if I have a set of particles, then each one of them gives me a delta function contribution to the right-hand side, right? So each one would be, so I'd get some sum of the mass of the ith particle times delta function x minus xi, right, if I have a collection of particles. And then you have this equation that del squared of minus 1 over 4 pi mod x minus xi equals delta function of x minus xi. Okay, so this is the usual formula that Newton used, that particles' mass create this gravitational potential. But if I take the Laplacian squared of this 1 over x, what it does is exactly reproduce the delta function. Okay, so this formula reproduces everything we want about the gravitational potential due to any mass distribution. So in particular, it implies, if I use this formula, h naught naught is minus 2 phi, then d squared h naught naught would be minus 2 d squared phi g. And so this would be minus 8 pi g, well, let's leave the minus sign there, minus d squared h naught naught is 8 pi g rho mass. And so this is equal to, so this is approximately 8 pi g T naught naught. Okay, remember I'm using C. So rho mass, rho energy. So T naught naught is rho energy, which is rho mass times c squared from E equals mc squared. And I'm using units where c is 1. Again, I'll put the c's back later by dimensions. So this is the equation we want, that the Laplacian acting on h naught naught is 8 pi g times t naught naught. If we had that, then we would recover Poisson's equation, and then from the geodesic equation, we recover all the motion of particles in gravity. Now, this is not a very good equation. It has these 0, 0 indices around, so it's not a tensor equation at all, but maybe it's the 0, 0 component of a tensor equation. So this could be the 0, 0 component of a tensor equation x mu nu, and this is constructed from g and the derivative of g and the second derivatives of g, some tensor. We already have an idea that it's the Riemann tensor somehow. The curvature of space-time should be represented by a tensor. It's got to be a symmetric two-index tensor. And this, on the right-hand side, we're going to have 8 by g t mu nu. So you see how Newton's constant has come into this equation. Einstein's theory doesn't improve on Newton's in that sense. It just takes the same constant and puts it into the equation. But that's our guess as to the equation we want. So what we want is some tensor, x mu nu, constructed from the metric and its second derivatives, and up to second derivatives, which reduces to this quantity in the Newtonian limit. So x mu nu Okay, so we're going to require that the x mu nu is built only out of the g. G, first derivative of g, second derivative of g. We don't want any more than second derivatives of g. Can you tell me why? Why do we want an equation which involves no more than two derivatives?
Dimensions?
Sorry?
Dimensions?
Dimensions, no.
Isn't it related to locality?
Dimensions is actually a good argument because this has two derivatives, right? And if we involve more than two derivatives, maybe we're going to get higher derivatives. However, you could always imagine that you add dimension-full constants, right, with more derivatives. So yeah, it's a very good argument that the dimensions of what we want only involves two derivatives, so why introduce anything else? I mean, g was dimensionless. We want to write down something only with two derivatives. If I do anything else, I'm going to have to introduce a dimensionful scale, right? So I would write something like L, some new scale, times a gradient. That's dimensionless, okay? So it will be a bit arbitrary. And in fact, that's what string theory does. So string theory introduces a new length scale, and the resulting Einstein equation is not Einstein's equation. It has extra terms like that. There's another reason that when you write down equations with more than two derivatives, very often they have instabilities. Okay, physics, for some reason we don't fully understand physics. All the equations of physics are only expressed in up to second derivatives. And there's a theorem called Ostrogradsky's theorem. And I encourage you to look it up. I always assumed this theorem was some very modern and powerful mathematical theorem until I looked it up. And when you looked it up, I think Ostrogradsky was working in the 1830. Okay. In Hamiltonian mechanics. Is some Russian doing Hamiltonian mechanics in 1830, and he proved that if you have more than two derivatives in the equations, then generically you have instabilities. You certainly have a lot more solutions because now you have more derivatives. More derivatives gives more arbitrary solutions, and in general that's dangerous. Okay, so anyway, this is consistent with being minimal. Clearly, we need at least two derivatives because of dimensions. So let's try and get away with the least we can possibly get away with. We need second derivatives. By dimensions. Well, we obviously need second derivatives because they're there. We obviously need second derivatives because this is g. So we're going to need its second derivatives. And obviously also we have the Riemann tensor lying around. It's just Riemann's gift to Einstein. Okay, there is a natural tensor. It's the unique one you can make out of two derivatives of the metric. And so, you know, God, wasn't Einstein dumb? He just had to take it off the shelf and use it, right? 100 years after Riemann, or almost 100 years after Riemann worked it out. Now, only problem is the Riemann tensor has four indices. Now, my only problem is I have to remember the definition of the Riemann tensor. Let me see. So, Riemann. Basically, we defined it. You'll have to remind me of the sign. But we defined it by taking the commutator of two covariant derivatives on a vector. And if you remember, that's obviously a tensor, because the whole point of the covariant derivative is it takes a tensor to a tensor. What is not so obvious is that all the derivatives of V cancel, at least when the connection is symmetric, when there's no torsion. All the derivatives of V cancel. And what we're left with is this. If I have the sign right, you'll correct me. So these are the two derivative indices coming last, and then we have sigma lambda. Sigma is down here. V lambda. Is that the right? Did I get that sign right? Okay, so that was the definition of the Riemann tensor, and we expressed it last time in terms of the connection. In fact, connection and its derivatives, and the connection involves first derivatives of the metric. So Riemann obviously involves second derivatives of the metric. Now, we won't actually need the explicit form, but we'll need some identities. In fact, before doing that, let's just make a couple of guesses as to what x mu nu is. Let's just make a guess. What would be the most naive possible thing you could guess for x? Two derivatives of the metric. Right? Well, let's just write down two derivatives of the metric. D lambda, g mu nu. Looks good. What's wrong with that? Symmetric, two derivatives of the metric. Yeah, too bad. So that's just an identity. It's 0, so no good. So Einstein went through many games with what to put on the left-hand side of the Einstein equations, and but this one doesn't work. What we want, so remember what we want is that x mu nu should be 8 pi g t mu nu. So we would like the field equations. We would like to write the field equations as, okay, where x depends only on g. Now, and this is where Einstein made his first mistake. He tried to write something down using Riemann. So again, another failure, but let's try this. I've got this tensor r lambda sigma mu nu, which depends on g, first derivatives of g, and second derivatives of g. What can I do with it in order to make a symmetric tensor x? What could I do? I've got a 4-index tensor. How do I make a symmetric tensor? Now, you could see some symmetries of R are sort of obvious immediately. R is antisymmetric under these two indices, right? So I cannot contract that with a G because this is antisymmetric. So I can't contract these two with a G, otherwise I'd just get 0. But what I can do is contract those two indices, this with that. And so this is R sigma mu. And indeed, it does turn out to be symmetric. This is the Ricci tensor. I mean, if what Einstein did was easy, what Ricci did was extremely easy. Riemann gave him the tensor and he just put a G there and got it named the Ricci tensor. Okay. He did a lot more, of course. I'm just joking. But so this turns out to be symmetric under sigma goes to nu. I'm not going to prove that. That's proved in all the textbooks, that if you work out the Riemann tensor, it is symmetric under those, or this contraction of it is symmetric. In fact, it's also in the printed notes. There's a proof of that. So the first thing Einstein did is just put x mu nu equals r mu nu. Okay, this turns out to be wrong as well. Einstein's first attempt x mu nu equals r mu nu, or proportional to r mu nu. This was wrong. And there's a famous photo of Einstein next to a blackboard, and on the blackboard is written the Einstein equation except with r mu nu instead of g mu nu. So I'm sure he wanted to get that expunged from the history books, but it was too late. So there was a furious debate, and then he corrected it. But let me show you the correct version. So to get to the correct version, you've got to realize that the defining property of T mu nu is that it is conserved. What does that mean? Covariant derivative of T mu nu equals 0. Okay, this is the basic property T mu nu must satisfy in order to be called a stress energy tensor. Okay, so if my T mu nu satisfies that equation, the covariant derivative of 0, that's enough to ensure that in any local coordinate system where g equals eta, or just in the neighborhood of a point where g equals eta, and the first derivatives of g vanish, so the connection vanishes, near such a point, this is just reduces to the ordinary energy momentum, ordinary stress energy conservation equation in flat space. So this is very, very important. We can't really write down a consistent equation without using this T, but the T has to satisfy this in order to even be called a stress energy tensor. So that means that if the right-hand side satisfies that equation, well, the left-hand side better satisfy it as well. Oops. So if we're going to set something equal to the right-hand side, we have to ensure that its divergence, its four divergence, is also 0. So to obtain a consistent equation, we must have d mu of x mu nu equals 0 as an identity. Okay, otherwise the equation would be mathematically inconsistent. We certainly don't want that. So the question is, can you make a tensor out of the Riemann tensor which satisfies this equation? And I think at the time of Einstein's work, I'm not sure the answer was known. I'm not sure anybody had particularly phrased that question. And so he had to play around with the definition of the Riemann tensor and try to find this x. And the x he found is called the Einstein tensor. Okay, so how do we do this? We start from the Bianchi identity. So what's the Bianchi identity? The Bianchi identity follows from the fact that whenever you have covariant derivatives, you can write down an identity involving 3 of them. You see, if x involves 2 derivatives, this is an equation in 3 derivatives. So we need some identity in 3 derivatives. And those of you who've done any theory of algebras will recognize this equation.
It's like the identity. I'm not sure what.
What's that equation called? This is the Jacobi identity. Okay, so the Jacobi identity, which holds for any algebra, which is, let me see, I've forgotten the terminology, but basically it's where A, B, C is uniquely defined. If you just write out all these terms, you'll find they all cancel. So we can start from this, and from here, all I do is introduce a vector. So let us introduce some vector, v sigma. And one can prove from this that R sigma rho mu nu semicolon kappa plus R sigma rho nu kappa semicolon mu plus R sigma rho kappa mu comma nu, sorry. I'm just cycling these last indices. So the nu goes first, and then the kappa goes first. And the sigma rho are unchanged. The notation here is that semicolon nu is equal to covariant derivative. Okay, so we use a comma nu to be the ordinary derivative. Comma nu is d nu, and semicolon nu is covariant derivative. So you can see it's quite a painful equation because you've got this covariant derivative acting on 4 index objects. So there are going to be 4 connection terms with connections in it, right, in each one of these. But the origin of the identity is something completely straightforward. Whenever you do algebras, the Jacobi identity is always one of the fundamental facts you have to be consistent with. And from this Jacobi identity, so you can see basically what I'm going to do is apply this operator here, and that'll give me Riemann. And then I'll take a derivative of Riemann and a derivative of this guy. And the derivative of this guy is going to cancel among all 3 terms. And all I'll be left with is the derivative of the Riemann tensor. There are 3 of the terms, and that's what they are. So that's the Bianchi identity. And now what we're going to do is contract it. So let's take that equation. I don't want to do it over here because it might be hard to see. Let me lift it up. So what I'm going to show you is that straight from the Bianchi identity, we can construct a tensor X, which is covariantly constant, that the covariant derivative of it is 0. Actually, whose covariant divergence vanishes, I should say. It's not any covariant derivative, it's the divergence. Okay, so what do I do with this? Well, it's got 5 indices, this equation. Let's start getting rid of some indices. So let's multiply this. So this is Bianchi. So let's take Bianchi and multiply it with G sigma nu. So that means you contract sigma with mu. Now what you can use is that the covariant derivative of G is 0, right? That was metricity. What this means is that I'm allowed to push the G through derivatives freely. I never get any extra terms through. So I can move G through derivatives, through covariant derivatives, and I never get any extra terms. Okay, so the G, even though it depends on X, I can actually push it under that kappa derivative. And what I'll get is, so sigma mu contracts the first and the third index, and R sigma rho mu nu with the first and the third contracted is this, which is the Ricci tensor. Okay? So the first term gives me the Ricci tensor. So this gives me R rho nu comma kappa, semicolon kappa. The second term, I'm contracting sigma with mu. We'll just leave it as it is. Sigma rho nu kappa sigma. The third term, I contract sigma with mu. Now we're going to need, so I'm contracting the first with the fourth, but remember this guy's antisymmetric under the third and the fourth. So I can flip these two with a minus sign, and I'll get the Ricci tensor back again. So I'm getting R, so sigma with mu, so I've got rho kappa, semicolon nu, equals 0. Okay, so that's an identity that follows from the Bianchi identity. Well, that's better, because I only have 3 free indices. But really, what I want is an equation like this, with only 1 free index. Right? So I just do another contraction. So let's multiply this time with G nu rho. So remember, R mu nu, or R sigma rho, was defined to be R lambda sigma rho. That's the Ricci tensor. If I contract this with a G, I can make a scalar. G sigma rho, R sigma rho. This is called the Ricci scalar. So Ricci got credit for 2 things by doing the same thing. Okay. All right. So if I contract R with G, so as I explained, the Ricci tensor is symmetric under rho and nu. So I contracted, I get R in the first term. I can bring this G under the derivative because it is covariantly constant. And then here, G nu rho, again, I'm contracting these two. Now I've got to use a symmetry of R that I haven't derived, I'm afraid, but we're going to have to use that R sigma rho nu kappa is equal to minus R rho sigma nu kappa. So the Riemann tensor is antisymmetric on the second two indices and also antisymmetric on the first two indices. Okay, that's derived in the notes. And so because of that, when I contract nu with rho, I can think about this as minus rho sigma rho kappa sigma. So what I've done here is flip the rho with the sigma. Riemann is antisymmetric under flipping those two, and nu with the rho, yeah, so that's like nu with nu kappa sigma, and this is Ricci tensor sigma kappa sigma. I can prove these symmetries. Maybe I'll do it next time. I'll prove the symmetries of R. So I had to use it here. This one is R. I contract rho with nu, so rho kappa rho. Let's call them sigma. Well, okay, so I get this. So by contracting this equation with G, this term gave me R. This term, I contracted the nu with rho. So I contracted the second and the third. But I'm telling you that I could flip the second with the first and get a minus sign. And then I would be contracting the first with the third, and that is the Ricci tensor. Here I have the Ricci tensor as well. And so what you can see from this is that R sigma kappa semicolon, well, R sigma kappa is this term. This term is the same with a factor of 2. And so we have minus 2 times that. And then this term I can write as follows, plus R G sigma kappa sigma equals 0. And so if I multiply with minus a half, what I get, and I'll raise an index, R sigma kappa minus 1/2 G sigma kappa R semicolon sigma equals 0. Okay, so X sigma kappa defined to be R sigma kappa minus 1/2 G sigma kappa R obeys covariant derivative d sigma X sigma kappa equals 0. Okay, so I had to use one fact there, which is that the Riemann tensor is antisymmetric under the first two indices as well as the second two indices. That's not obvious, and I'll show you how to prove that next time. Okay, so this is the X. And I think you'll agree it's rather clever how from something obvious, the Jacobi identity, just by contracting with G's, you create this tensor X, which is called the Einstein tensor. So this is the Einstein tensor, and it's called G, capital G mu nu, sigma kappa. So now we have a candidate equation which has a chance of being mathematically consistent. Candidate equation is g mu nu equals 8 pi g t mu nu, where g mu nu is r mu nu minus 1/2 g mu nu r, and r mu nu is Riemann lambda mu lambda nu, and r is r lambda sigma lambda sigma. Okay, so these are things just constructed from Riemann. You do have to be careful about the order of these indices, even when they're up and down, because Riemann is antisymmetric on some indices and symmetric on others, actually. Again, I'll explain that tomorrow. But here's the equation. And now all we have to do is something quite simple, which is determine, you see, let's put, what do I call it? Let's call it A. Because I haven't justified the proportionality constant being 1 yet, all I said is that whatever I put on the left-hand side needs to be, needs to satisfy d mu, g mu nu, d mu, a g mu nu equals 0, right? So I don't know, that doesn't fix the constant. A is a constant fixed by checking that the left-hand side, checking the correspondence with Newtonian limit. Okay, we've not argued for that constant, but luckily we've done enough to actually figure out the constant, almost enough, because we know the relationship between grad squared h naught naught and rho, and that'll be enough to fix the constant. So let's see. I don't know if I'm going to have time to do this. I think rather than rush, I will do this tomorrow morning. So tomorrow morning we will fix that constant a. In fact, a will turn out to be 1, and this equation will reproduce exactly del squared h naught naught is so h naught naught is minus 2 phi, and so it'll turn out that did write this down somewhere. Can't see it because of the light. Yeah, minus del squared h naught naught is 8 pi g t naught naught. Okay, and so the left-hand side will equals this if a equals 1. Okay, and that's that. So that will show us that we completely reproduce Newton's theory from in the appropriate limit. Yeah.
Just to be abundantly clear, that the Jacobi identity, that expression is equal to 0, right?
Yes, that is identically 0 for any algebra which satisfies this. All you need to do to prove that identity is write it out. It's a good exercise just to do that once in your life. Write down these terms. All right, so I'll write down the first one, d lambda minus d lambda d nu. Okay, minus d nu d lambda minus d lambda d nu times d mu. That's the first term, right? So every term involves three derivatives. If you write them all out, they'll all cancel. The only thing you need to do the only assumption you need to make in order for these things to cancel is this one, that d mu, d nu, d lambda equals d mu, d nu, d lambda. In other words, it doesn't matter which order you take the derivatives, and that law is satisfied by the covariant derivative. Okay, so just write down all these terms. You'll see they all cancel. Yes. Was that the question? Oh, sorry.
Yeah, I was just clarifying because it doesn't say equal 0 at the top, but I was pretty sure that's what the Jacobi identity said.
Oh, yeah, very good. Yeah, so the first line should be 0. Thanks. The Jacobi identity is that this is 0.
Yes. How do you know that the covariant derivative acting on x has to be 0, like on its own? Why can't you just say that's an equation of constraint on?
Well, you wanted to write something down. We wanted to write down some equation. We want to write down this equation, and the idea is the following. You see, go back to John Wheeler's slogan. Matter tells, or energy tells space how to curve. That's what this equation is doing. So this measures the curvature of space. And space tells energy how to move. That's the d mu t mu nu is 0. So whatever we want this t mu nu, when we work out these equations, this should be 0 by the equations of motion of the matter in any space-time metric. So you imagine the fixed metric, and I use the equations of motion for the matter. They should imply energy and momentum are conserved, right? So you want this to be true for all g, right? So it doesn't matter what the g is. So now you look at this equation. Well, if this is true for all g, and this is not true, if this is not true, you just have an inconsistency. You got something non-zero is something 0. Right? So you could say, why do I insist this be true for all g? And that is the equivalence principle. Because the equivalence principle says, take the laws of flat space-time physics, and in flat space-time physics, you always have an energy-momentum tensor. And when you go to curved space-time, all I do is stick g's in where I had eta, and I change this derivative to covariant. That's the equivalence principle. So flat space-time physics becomes curved space-time physics.
What I mean is, why can't you just say that covariant derivative acting on x equals 0 is just another equation of motion?
No, because it's just inconsistent. So I'm saying if I use the equivalence principle to define how matter moves in a metric, then automatically this is 0 for all g. Now you're telling me what happened if I introduced a tensor there where this is 8 pi g, the field equations, right, where this is 0. I'm insisting this is 0. That's how I put matter into a curved space, by insisting this is 0. But you're telling me this is not 0. Well, you just got an inconsistent equation. So you can't have 0 equal something non-zero. Otherwise, you're out of luck. So yeah, it's really the equivalence principle, insisting that the matter follows the equivalence principle. The equivalence principle says replace eta with g, derivatives with covariant derivatives, and that's it. And whatever equation you had before has to still hold. Yeah.
Why do you call it an inconsistency instead of? Why do you call that an inconsistency instead of?
Well, if I have something non-zero equals something zero, that's an inconsistency.
Instead of requiring that a solution satisfies this property.
No. If something non-zero equals something zero, so you see, I'm saying for the right-hand side, whatever G is, it has to be zero. That is how you define the matter in a given metric. Therefore, whatever G is, the left-hand side has to be zero. Otherwise, you have an inconsistency.
You're solving for x, right?
I'm not solving for x. I'm solving for G. I mean, x is a quantity depending on G. X depends on G. Right? So, whatever G is, the right-hand side obeys this equation. It therefore follows that whatever G is, the left-hand side has to satisfy this equation. Otherwise, it's inconsistent.
I just don't see why I need to pose that in the level of the equation instead of in the level of the solutions.
Yeah, let me think about it. So So let me put it okay. So what you're basically saying is that there might be so some G's may not satisfy the equation, right? And those would be G's for which this is not zero, and they don't satisfy the equations, right? So you might say that. The trouble is you would be putting a constraint on the G's which has absolutely nothing to do with the matter. You see, in Einstein's framework, I could introduce any kind of matter. I could throw particles and fields, and when I solved so what I'm saying is that by imposing such a constraint, I mean, you would be saying that there are certain G's which are not allowed. In Einstein's theory, that is not true. Any G is allowed, in principle, but it depends on the matter. So you're sort of throwing in an extra constraint, which would be very, very artificial. It would say, independent of anything to do with the matter, I can rule out a large number of G's. That would be pretty terrible, because it would say, somehow I look at the space of all G's and I have to just a priori throw out many of them. Right? But you're right. In principle, you could do that, but I guess Einstein didn't want a theory like that. He wanted a theory which, in principle, allows almost any G, and then the G is fixed by the matter. So you have so much freedom here to design matter. You can put particles or fields or anything you like. So you really don't want to artificially constrain the metric in some other way. You want the matter to determine the metric. You know, otherwise you could not really argue that energy tells space how to curve, because you had some other equation that told space you cannot curve in this and that way. You don't want that. It's really just the energy tells the space how to curve. Yeah, good questions. Any other questions? I think you need a break. Okay, so I'll see you tomorrow. I'll tell you a little bit more about the Riemann tensor and finish this derivation.